We're now going to formalize the linear algebraic information we need. So we're going to start by showing if you have a field extension, one's a vector space over the other. So suppose L over K is an extension, then the operations multiply, right? K is a subfield of L. We can think about it as a subfield of L. So I can multiply two elements of L, and that's all this is, just multiply them. And L is a field, so you can add. So the second operation is just addition. Okay? So in the previous example, like we had q sitting inside of the q adjoining the square root of 2. This we would write it, of course, as an extension like this. Of course, if you have any rational number, you can multiply it by any element in this larger field, right? You just scale it. And if you have any element in a larger field, you can add them because it's a field. So that's all this is saying is, hey, look at the operations you're given, but I only want to think about scaling on the left by elements of the base field. The conclusion then is these operations define on L the structure of a K vector space. So a vector space over K. Okay. So what is the axioms for a vector space? So I'm going to say take a moment and pause and just look at any article. Maybe, I mean, Wikipedia is a good source for this. Look at the axioms for a vector space. Then open up a separate page and look at the axioms for a field. Keep in mind L is a field here. L is the field. And then ask yourself, which of those field axioms will give us the axioms for the vector space, and are we missing any axioms for a vector space? And you're going to find that you're missing absolutely nothing. In fact, there are more axioms for fields than there are for vector spaces. In particular, fields allow for multiplication not just by subfields and the larger field, but all elements of the field. And fields also have multiplicative inverses. Okay, so to say something is a field is a stronger condition than to say that a structure is a vector space. Okay, so I'm not going to prove it, but go look at a proof, or not a proof, but go look at the axioms and then just put them side by side, and you'll see that you get all the axioms for a vector space. Okay, so moral homework, do that. Now, there is nothing here that requires that the extension be finite. So for example, C is an R vector space. Okay, that's a finite extension because, well, you just need 1 and I as in the basis. We'll revisit this here in a second. But C is also a Q vector space. Because Q is a subfield of C. C is an extension of Q. It's a particularly nasty extension of Q in that as the size of a basis is uncountably infinite, but it is in fact a Q vector space. So this was like a finite example, and this is an ungodly infinite example. All right. Now the important, well, there's several important consequences of it being a vector, field extensions being the larger field being a vector space over the smaller one, but perhaps the most important thing that we get from that is the notion of a degree. So definition, I guess I highlight my examples in blue. So let's do blue here. And then green for our definition. Okay, so given an extension, and by extension, of course, I mean in the context of this class, so field extension, the degree of L over K, which is denoted by brackets L colon K, is the dimension of L as a K vector space. Or in the notation of our motivating example from earlier, the degree of L over K is the dimension over K of L. All right, and so that's that. So let's do some examples of computing this. I think it would be helpful to start with the ones from before, because we already computed them. So the degree of Q adjoin root 2 over Q is 2, as 1 in root 2 is a basis. And of course, the dimension, if you've forgotten, this is just the size of a basis. Any basis. What else did we compute? We computed the degree of Q adjoin the fourth root of 2 over Q adjoin the square root of 2. We saw that was also 2, as 1 and the fourth root of 2 is a basis. And then we also saw that Q adjoin the fourth root of 2 over Q has dimension, well, has degree 4, as we multiplied these and those were a basis. And the basis has size 4. Okay, so we saw those examples already. One of the examples I wrote earlier was C and R. So R is certainly an extension of C. And this is 2, as you can express any complex number as a combination of 1 and I. So this is a basis. What other fields have we looked at? I think we've looked at things like Q adjoin root 2, root 3 over Q. Okay, this is 4 as well, as 1 root 2 root 3, and then we have to look at root 6 as a basis. And so on and so on. All these are powers of 2. Let me do a non-power of 2 real quick. Another very important field that we're going to see again and again is adjoining the cube root of 2 to Q. And that has degree 3, as you would expect from your homework, one, what we called alpha, which is the cube root of 2, and then alpha squared, which is the cube root of 4, is a basis. These are all examples of degree, and the way in which you compute the degree is you look at the size of a basis, because that tells you the dimension.